Here we look at a question on Born-Haber cycles, the perfect ionic model. And this will hopefully apply some of the knowledge that you looked at in the two videos that I made on Born-Haber cycles and perfect ionic model. We've been given some enthalpy information there, which is something we'll use a little bit later on. First question, though, is asking you to work out the bond enthalpy of a Cl-Cl bond. So how do you do this? Well, we get that answer from this enthalpy of atomization. Now, the enthalpy of atomization is as follows. It's half Cl2 to produce Cl, and that there is equal to plus 121 kilojoules per mole. That is my enthalpy of atomization. The enthalpy change to form a mole of gaseous atoms. But the bond enthalpy is breaking 1 mole of covalent bonds. So here is my bond enthalpy. So in my bond enthalpy, I'm forming 2 moles of chlorine atoms. So my answer is going to be double. My atomization enthalpy. So the answer to this is plus 242. Then it says to explain why the chlorine-chlorine bond enthalpy is greater than the Br-Br bond enthalpy. Well, let's consider a chlorine-chlorine bond. And this is my pair of electrons. And now let's consider a bromine molecule. And we can see that in bromine, the shared pair of electrons are much further away from the nucleus. There's also more shielding, but the key is they're further away from the nucleus. So the answer would be in chlorine, the bonding pair of electrons are closer to the nucleus. And then you need to justify it saying, therefore, greater attraction between nucleus and bonding pair of electrons. So that's what you would say for this one. In chlorine, the bonding pair of electrons are close to the nucleus. Therefore, the greater attraction between the nucleus and the bonding pair of electrons. So these chlorine atoms are obviously much smaller, less electron shells, and therefore closer to this bonding pair. Therefore, a greater attraction between this nucleus and the bonding pair of electrons. It says then suggests why the electron affinity of chlorine is an exothermic change. Any first electron affinity for any atom, whether it be oxygen, chlorine, fluorine, are always going to be exothermic. And it's just kind of an answer you need to learn. In the answer is there's a net attraction, and this is where you got to get the wording correct, between the chlorine nucleus and the electron being added. And that's kind of a set answer that you need to learn. Question D says the diagram below is an incomplete Born-Haber cycle for the formation of silver chloride. The diagram is not to scale. So we've got the elements and we've got the ionic solid. and we've got the gaseous ions, and we need to fill the rest in. And here you see we've got now lattice dissociation enthalpy. Remember, if the arrow went down, that'd be a lattice formation enthalpy. Well, what I would do first is I would atomize my silver, remember? Again, state symbols are absolutely vital. So remember, the first thing you atomize silver, then you would ionize silver, and make sure you add your electron. So that's the silver done, if you like. Then what you've got to do, you've got to atomize the chlorine. So you'd go then to Ag plus gas plus Cl gas plus electron, and obviously this enthalpy change here is the electron affinity, where this chlorine atom has gained the electron to form a chloride ion. So that is what you should have had, and again, if you've watched the video on Born-Haber cycles, that should be relatively straightforward. Then it says to calculate a value for the lattice dissociation of silver chloride. So in effect, this is what I want to work out. What I'm going to do now is I'm going to use the table earlier on to fill in the other values. So my enthalpy of formation of silver chloride is minus 127. The atomization enthalpy of silver is plus 289. The first ionization energy is plus 732. And the enthalpy of atomization of chlorine is plus 121. And the electron affinity minus 364. So I've got all the values that I need now to work out this enthalpy change. And now, remember, we're going to go in this direction. Heads of the arrows should meet, base of the arrows and heads of the arrows should meet. So any arrows that go in the wrong way, remember, the sign changes. If I'm going this way, then the 127 then becomes plus 127. And it is again plus 289 because the arrow's going the right way. And we've got plus 732 and plus 121. In fact, all these arrows apart from this one is going the right way, so that stays as minus 364. And again, you should be able to guesstimate this answer. It's a lattice dissociation enthalpy, so it's going to be a very big positive number, and it works out to be plus 905 kilojoules per mole. And again, if you've looked at the video on Born-Haber cycles, this shouldn't have caused you too many problems, a question like this. It then says, the enthalpy of lattice dissociation of silver chloride can also be calculated theoretically assuming a perfect Ionic model. What is a perfect Ionic model? Explain the meaning. And that is, it assumes 100% ionic character, or ions are perfect spheres. You could have also said no covalent character. Any of those would be absolutely fine. It then says, state whether you would expect the value of the theoretical enthalpy of lattice dissociation for silver chloride to be greater than, equal, or less than that of silver bromide. So what we're comparing then is the lattice dissociation enthalpy of these two. And again, in the Born-Haber cycle video, we said that as the size of the ion increases, the magnitude of the lattice dissociation enthalpy will decrease. So you would say then that the AgCl will have a greater lattice dissociation enthalpy than AgBr. Why is that the case? We've got to justify why. AgCl, or I should say, sorry, the Cl ions, chloride ions, are smaller than bromide ions. Therefore, chloride ions more strongly attracted to the silver ions. And that there is a very complete answer there. Okay, and again, we've looked at that when we looked at both the videos on the Born-Haber cycle and the perfect ionic model. The size of the ion increases, the magnitude of the lattice enthalpy will decrease. It then says, suggest why your answer to part D, part 2 is greater than the theoretical value. And the reason is because it assumes, I wouldn't say assumes, that's probably not the case, it's because it has covalent character. And we said, why is the answer greater than the theoretical value? As covalent character, and this increases the strength of the bonding. And again, that is covered in the video on the perfect ionic model. So there's a difference between the theoretical and the experimental value. Why? Because the experimental value calculated by Born-Haber cycles has covalent character, and this increases the strength of the bonding. So that there is a nice little exam question which covers and helps to apply some of the stuff that we've done in the videos on Born-Haber cycles and the perfect ionic model.